Hello, everyone. This is going to be a successive approximations example problem. So what we're going to do is go through and solve it. And in the process, we're going to talk about successive approximations and how you can use it to simplify problems under appropriate conditions. So here's our example problem. So we have a reaction, and you can see the equation for it here. Okay, so we're going to make ammonia from nitrogen gas and hydrogen gas, and it has an equilibrium constant equal to this quantity at some given temperature. So we don't know what the temperature is, but we don't really care. We just know that our equilibrium constant is temperature dependent, and so we have to be at a certain temperature. Now, what we're going to do is add 0.060 molar nitrogen gas and 0.040 molar hydrogen gas to the system, and we're going to heat them. And it's going to be it to this particular temperature. Now, what we want to do is calculate the equilibrium concentration of ammonia at this temperature. So, as we always do, the first thing is to set up an ICE table. So ICE just stands for initial, change, and equilibrium. Okay? And an ICE table is really the easiest way to keep yourself organized for a problem, and an equilibrium problem in particular, of course. So what I'm going to do is I'm going to write down our reactants. Okay, and I'm going to leave a little space and put our equilibrium arrows, and then I'm going to write down ammonia and all of these with their coefficients, of course. And then down the side, I'm going to write ICE. Okay, now I is initial. So what we do is we go up and we find the initial concentrations of our two reactants in this case. It could be products, but in this case, it's reactants. And all we do is just write them there, okay? Now, the problem doesn't give us an initial concentration of ammonia, so that means it's going to be 0, okay? So now we have to go through and write down the change, all right? Now, when you have an equilibrium system, then if you have 0 of something to begin with, you're always going to get some of it. There has to be some of everything at equilibrium. So that means this one is easy because we can just say plus 2x. We know we're going to get X amount, and since the coefficient of ammonia is 2, it's going to be 2x amount, okay? And we know that we have to use up some of the hydrogen gas and some of the nitrogen gas in order to make that ammonia. So notice that we have minus 3x for hydrogen gas, and that's because of that coefficient 3 in front of hydrogen, and there's a coefficient of 1 that's assumed in front of nitrogen. So we have minus x for nitrogen, okay? So the next thing we're going to do is just write out the equilibrium expression for each of these, okay? So basically, we just add them together. All right, so the next step is to build the equilibrium constant, okay? So what I'm going to do is go to the next page, and I'm going to write down these again. So here's our equilibrium expressions. So for nitrogen, hydrogen, and ammonia, just for reference, we have 0.060 minus, hold on, let's go ahead and do that, minus x, and then 0.040 minus 3x, and then 2x, okay? Now I'm also going to write down from the previous page that our equilibrium constant is this quantity at the temperature that we are doing this reaction. Okay, so now what we're going to do is set up our equilibrium constant expression. Okay, so I just put the value of K there, and it's equal to products over reactants. So we have to do 2x, right? And then remember, oh yeah, let me write those coefficients. Remember, we take it to the coefficient power. Okay, so that's going to be 2x squared For nitrogen, it's going to be 0.060 minus x, and just to the first power, okay? The coefficient is 1. 0.040 minus 3x to the third power there. All right. Now, that's kind of an ugly expression, isn't it? And so what we would really like is a way to simplify this so it's easier to solve, okay? So now we have a few things to notice here. Notice that the concentrations that we start off with, 0.06 molar and 0.04 molar, are much bigger than our equilibrium constant, okay? So I'm going to write initial concentrations are much larger than K. Another thing is that K is generally small, okay? And since the equilibrium is the equilibrium constant is small, any quantity of change, so like x is going to be small too. Okay, so it's because the equilibrium constant is small, that means any amount of change is also going to be small. So what that tells us is that we can actually ignore or basically put in 0 for the x that is compared to an initial amount, okay? So in other words, this x is likely to be much smaller than 0.060 and much smaller than 0.040. So we can just put in 0 for that, and we can solve the problem and solve for this x. So let me change the color again. So this is the x we're going to solve for. And then we're going to get a very nice approximation, okay? And so let's go ahead and do that. So we're going to take 0.0010, and that's going to be equal to 4x squared, okay? And it's going to be 0.060 times 0.040 to the third power, okay? And now remember, we're going to solve for that x that's in the numerator. So let's go ahead and just rewrite that, okay? So we can just take, let's take 0.0010 and we're going to multiply it by 0.060, multiply that by 0.040 to the third power. So those are just numbers, so just multiply them all together, and 4x squared. Now let's go ahead and divide both sides by 4, and we're going to end up with x squared equal to 9.6 times 10 to the negative 10, okay? We want to take the square root of both sides of that, and we are going to end up with 3.0983 times 10 to the negative 5. Now, we don't need to keep all of those decimal places, so we can actually just make it 3.1 times 10 to the negative 5. And that's really because we see this very, very small exponent, okay, so to the negative 5. So this is actually a very small number. So that little bit of rounding isn't going to make a difference, okay? Now, we do have to do a little bit of analysis to make sure that we're not doing something inappropriate with our assumption. And so I'm going to go ahead and just put a square around it. So you can see 3.1 times 10 to the negative 5. And let's compare that to, we're going to compare to 0.060. That's very small compared to that, right? And also very small compared to 0.040. So this is actually a valid assumption. And you also look at our equilibrium constant, and even it is much larger than this x value. So that tells us that our assumption is just fine. So we can go ahead and use it. So now when we want to calculate the concentration of ammonia in the system, remember it was 2x from our equilibrium expression. So we're just going to take our value for x, multiply it by 2. Oops, that should be negative 5. And we end up with 6.2 times 10 to the negative 5 molar. Okay, now that is our final answer. But if we wanted to check ourselves, okay, so if we really wanted to check and make sure that we did things properly and didn't make an inappropriate assumption, we could put in this quantity. We want to put in the x, 3.1 times 10 to the negative 5, 0.040 minus 3 times 3.1 times 10 to the negative 5, all to the third power. And if we do that, we should get x very close to 3.1 times 10 to the negative 5. So that's another way we can check ourselves and make sure that we didn't make an inappropriate assumption.